In this section, we will look at examples of radical equations and solving equations that are in quadratic form. Our first example is the cube root of 1 minus 2x minus 1 equals 0. So the first step is to always isolate the radical. So here we will add 1 to both sides, and we'll end up with the cube root of 1 minus 2x equals 1. Now here the root is 3. So to get rid of the radical, we will raise both sides to the third power. On the left-hand side, we're left with what's underneath the radical, 1 minus 2x, and then 1 cubed is 1. So we have 1 minus 2x equals 1. We want to get x by itself, so we'll subtract 1 from both sides. So we have negative 2x equals 0. We'll divide both sides by negative 2, and x equals 0. With radical equations, you really do need to get in the habit of checking your solutions, though. It is more important when we have even roots and when we have x appearing more than one time, but it's a good habit to always be in. So let's check our solution. I'm going to always go back to my original equation and substitute in my value for x. So the cube root of 1 minus 2 times 0 minus 1, does that equal 0? The cube root of 1 minus 0 minus 1, does that equal 0? The cube root of 1 minus 1, does that equal 0? The cube root of 1 is 1, so 1 minus 1, does that equal 0? 0 equals 0, so yes, our solution is x equals 0. Our next problem is a little bit harder. Here we have 2 plus the square root of 12 minus 2x equals x. Again, we'll start off by isolating the radical. So let's subtract 2 from both sides. Now we'll have the square root of 12 minus 2x equals x minus 2. To get rid of the radical, to undo that, we need to square both sides. So I will raise both sides to the second power. Notice on the right-hand side, we do need to add parentheses around the whole right-hand side, x minus 2, and square that whole entire side. We can't just square the pieces individually, or the terms individually. So on the left-hand side, when we square that radical, we are left with what's underneath, the 12 minus 2x. And when we square x minus 2, remember that's x minus 2 times x minus 2, we end up with x squared minus 4x plus 4. This is a quadratic equation because I have a quadratic term. So I'm going to move everything to the right-hand side and have 0 on the left. So I will subtract 12 from both sides. I will add 2x to both sides, and I'll end up with 0 equals x squared minus 2x minus 8. So this right-hand side will factor. I need to find numbers that multiply to negative 8, but add to negative 2. Negative 4 and positive 2 work, so I can fill in my parentheses with x minus 4 and x plus 2. Now I'll use the zero product property and set each factor equal to 0. So x minus 4 equals 0, or x plus 2 equals 0. And I'll solve each of those equations for x. So I'll add 4 to both sides in the first equation, and I'll get x equals 4. I'll subtract 2 from both sides in the second equation, and I'll end up with x equals negative 2. I'm going to go check on the next slide. So my original equation, remember, was 2 plus the square root of 12 minus 2x equals x. We just found x equals 4, or x equals negative 2. So now let's check x equals 4. Substituting that in, we get 2 plus the square root of 12 minus 2 times 4. Does that equal 4? Or 2 plus the square root of 12 minus 8. Does that equal 4? 2 plus the square root of 4. Does that equal 4? The square root of 4 is 2, so 2 plus 2. Does that equal 4? Yes. 4 equals 4, so 4 works. 4 is a solution. Now let's check x equals negative 2. Substituting in 2 plus the square root of 12 minus 2 times negative 2. Does that equal negative 2? 2 plus the square root of 12 plus 4. Does that equal negative 2? 2 plus the square root of 16. Does that equal negative 2? The square root of 16 is 4. So 2 plus 4. Does that equal negative 2? No, 6 does not equal negative 2. So negative 2 is not a solution. Remember, we called that extraneous. So here, the only solution is x equals 4. Let's look at a slightly harder example. The square root of 3x plus 1 minus the square root of x minus 1 equals 2. So again, we need to start off by isolating a radical. But here we have two radicals, and so we have our choice. We can isolate either one. I'm going to move the second one to the right-hand side. So I will add the square root of x minus 1 to both sides. So on the right, I'm left with on the left, I'm left with the square root of 3x plus 1. And on the right, I have 2 plus the square root of x minus 1. Now I will square both sides. So the left side, okay, the square cancels out the square root, and I'm left with 3x plus 1. But it is a little more complicated squaring the right-hand side, because this means we are multiplying 2 plus the square root of x minus 1 times 2 plus the square root of x minus 1. Distributing, we get 2 times 2 is 4. 2 times the square root of x minus 1 is 2 times radical x minus 1. The square root of x minus 1 times 2 is again 2 times the square root of x minus 1. And then the square root of x minus 1 times the square root of x minus 1 is x minus 1. Let's combine like terms on the right. So I can combine my 4 and my negative 1 and get 3. I can combine both of the radical terms and get 4 radical the square root of x minus 1. And then I still have this x term, so plus x. Well, now I need to go back to my first step, and I need to isolate a radical, the only radical now this time. So we'll get this radical by itself. Let's subtract 3 from both sides. Let's subtract x from both sides. So we now have 2x minus 2 equals 4 times the square root of x minus 1. So ideally, we'd like to be able to divide both sides by 4 to truly isolate the radical, but it's okay to have a number that's being multiplied by the radical. I will still try to make it smaller. If I divided everything by 4, I'd have fractions, and that'd be okay, but it would introduce a little bit higher level of difficulty. But I can make my numbers smaller by dividing everything by 2. So let's divide all 3 of our terms by 2. I'm left with x minus 1 equals 2 times the square root of x minus 1. And at this point, we will now square both sides. Let's do that on the next screen. So this is what we're trying to do. If I square the left-hand side, remember that's x minus 1 times x minus 1. We'll have x squared minus 2x plus 1. And on the right-hand side, we need to square the 2, which is 4. And then if we square the radical, we get x minus 1, and I do need the parentheses here. Now I'll distribute on the right-hand side, so x squared minus 2x plus 1 equals 4 times x is 4x. 4 times negative 1 is minus 4. I will move everything to one side and have 0 on the other. So I will subtract 4x from both sides, and I will add 4 to both sides. I'll be left with x squared minus 6x plus 5 equals 0. I can factor this left-hand side. So what are numbers that multiply to 5 and add to negative 6? That would be negative 5 and negative 1. So I can fill in my parentheses as x minus 5 times x minus 1. That product equals 0, so I can use the zero product property and set each factor equal to 0. So x minus 5 equals 0, or x minus 1 equals 0. In the first one, I'll add 5 to both sides, x equals 5. In the second equation, I'll add 1 to both sides, x equals 1. So these are my two potential solutions, but now we need to check them. So let's first check x equals 5. And I'm going back to my very original equation and substituting in. So the square root of 3 times 5 plus 1 minus the square root of 5 minus 1, does that equal 2? The square root of 15 plus 1 minus the square root of 4, does that equal 2? The square root of 16 minus the square root of 4, does that equal 2? The square root of 16 will be 4, the square root of 4 will be 2. So 4 minus 2, does that equal 2? 2 does equal 2. So x equals 5 is the solution. Now let's check x equals 1. The square root of 3 times 1 plus 1 minus the square root of 1 minus 1, does that equal 2? The square root of 4 minus the square root of 0, does that equal 2? The square root of 4 is 2, the square root of 0 is 0. So 2 minus 0, does that equal 2? 2 equals 2, yes, that's true, so that one works as well. So both solutions work here. So we have two solutions. Be aware you can have both of them work, one of them work, or neither of them work. So don't always assume that it's only going to be one that works and one is extraneous. So I know that my lab Math and Mastering likes to often have you enter solutions separated by a comma. So you could also write that as x equals 5 or 1 with a comma separating the 5 and 1. Okay, so let's look at another example. Here we have 3x minus 5 all raised to the 1/2 power equals 2. Well, this is a radical equation because that's what we have when we have rational exponents. Remember, something to the 1/2 power is the same as the square root of that expression. So we will start by raising both sides to the reciprocal power, in this case 2. So we will square both sides. And the reason why that works is if we take a power to a power, our exponent laws say to multiply the exponents. 2 times 1/2 is 1. So we end up with just 3x minus 5 to the first power, which is 3x minus 5. And then 2 squared is 4. Now this is a simple equation that we can solve for x. We'll add 5 to both sides. 3x equals 9. Divide both sides by 3. And x equals 3. But remember, this is a radical equation. We should check our answer. So if we substitute that into the original, 3 times 3 minus 5, all raised to the 1/2 power, does that equal 2? 9 minus 5 to the 1/2 power, does that equal 2? 4 to the 1/2 power, does that equal 2? Well, 4 to the 1/2 power is 2. That does equal. So x equals 3 is our solution. Okay, this equation looks a little different. X to the 4th minus 10x squared plus 25 equals 0. Well, this is definitely not a radical equation, but it's not quadratic either because we have an x to the 4th term. But it looks very similar to a quadratic equation. So this is something that is considered to be in quadratic form. And we're going to use substitution, or sometimes called U substitution, to solve this. So I'm going to set u equal to x squared, which is my middle variable expression. And technically you don't have to use u. You can use any variable. You shouldn't use x because that variable is already in the problem. So any variable other than the one that's already in the problem. So u equals x squared, and then u squared will equal x squared squared, which is x to the fourth, which matches up with our other variable expression. So this is a proper substitution for this problem. So we will now substitute in. So the x to the fourth is replaced with u squared, minus 10 times the x squared is replaced with u, plus 25 equals 0. And now this looks like a normal quadratic equation. This one factors. It's a perfect square. So I can factor it to u minus 5 quantity squared equals 0. I can take the square root of both sides. U minus 5 equals plus or minus 0. But plus or minus 0 is the same thing, so we don't really need the plus or minus here. To get u by itself, I will add 5 to both sides. U equals 5. But you need to remember, we are not trying to solve for u, we need to solve for x. So we need to go back to our u substitution and solve back in for u. What was u equal to? U equaled x squared. So this becomes x squared equals 5. And now we need to solve for x. I will square root both sides, and I have x equals plus or minus the square root of 5. So I have two solutions to this problem: positive square root of 5 and negative square root of 5. Okay, let's look at something that looks more complicated. We have 2x plus 5 quantity squared minus 2x plus 5 minus 6 equals 0. Now, we could go and multiply this all out and combine like terms and then solve the quadratic equation, but we could also recognize that this is in quadratic form. I can set my u equal to my middle variable expression, 2x plus 5. And u squared will be 2x plus 5 quantity squared. Substituting in, that makes this original equation turn into u squared minus u minus 6 equals 0. And this is a simple quadratic equation that we can solve by factoring. What are numbers that multiply to negative 6 and add up to negative 1? They are negative 3 and positive 2. Now we can use the zero product property and set each factor equal to 0. So u minus 3 equals 0, or u plus 2 equals 0. In the first equation, I will add 3 to both sides, so u equals 3. In the second equation, I will subtract 2 from both sides, u equals negative 2. But remember, we are not solving for u, we need to know what x is. So we need to solve back in and substitute 2x plus 5 where the u is. So the first equation becomes 2x plus 5 equals 3. And the second equation becomes 2x plus 5 equals negative 2. And both of these we will now need to solve for x. So in the first one, I will subtract 5 from both sides. 2x equals negative 2. Then I'll divide both sides by 2. X equals negative 1. In the second equation, I will subtract 5 from both sides. 2x equals negative 7. And then I will divide both sides by 2. And x equals negative 7 halves. So I have two solutions to this equation, negative 1 and negative 7 halves. Okay, let's look at another example. X plus 8 times the square root of x equals 0. Now, I could treat this like a radical equation like we did at the beginning of this screencast, but we could also recognize that this is in quadratic form. U could equal the square root of x, and then u squared would be x. When I substitute, that makes this equation turn into, or transform into, u squared plus 8 times u equals 0. I can solve this by factoring out a GCF of u, a greatest common factor of u, and what goes in the parentheses will be u plus 8. Still use my zero product property and set each factor equal to 0. So either u equals 0 or u plus 8 equals 0. So I already have the first one solved for u. The second one, I subtract 8 from both sides and I get u is equal to negative 8. But remember, we don't want to know what u is, we want to know what x is. So let's substitute the square root of x back in for u. First one becomes the square root of x equals 0. And the second one is the square root of x equals negative 8. In the first one, I will square both sides to get rid of the radical. So x equals 0. The second one, when is the square root of x going to equal negative 8? Well, if we are solving over real numbers, which we are here, there is no solution here. Or no real solution anyway. So our only real solution is x equals 0. If we did solve out the other one and get another possible answer, if we went back in and checked our answer, that would be extraneous. If we check x equals 0, though, in the original, 0 plus 8 times the square root of 0, does that equal 0? 0 plus 8 times 0, does that equal 0? 0 does equal 0, so yes, x equals 0 does work. But that is our only solution here. Okay, this one looks a little different. X to the 1/2 power minus 3 times x to the 1/4 power plus 2 equals 0. Well, this one is also in quadratic form. We could set u equal to x to the 1/4 power, which matches up with our middle term variable expression. U squared then will be x to the 1/4 squared, which is x to the 2/4, or x to the 1/2, which matches up with our first variable expression. So u squared is equal to x to the 1/2. Substituting in, we get u squared minus 3u plus 2 equals 0. Again, this is a quadratic equation that factors easily. So what are numbers that multiply to 2 and add up to negative 3? Negative 2 and negative 1. So we can write u minus 2 times u minus 1 equals 0. Using the zero product property, we'll set u minus 2 equal to 0 or u minus 1 equal to 0. Solving the first equation, we'll add 2 to both sides, u equals 2. Solving the second equation, we'll add 1 to both sides, u equals 1. Now we'll go back and replace the u with x to the 1/4 power. So x to the 1/4 power equals 2, or x to the 1/4 power equals 1. To get what x equals, we need to raise both sides to the reciprocal power. The reciprocal of 1/4 is 4. So x to the 1/4 to the 4th power is x. 2 to the 4th is 16. We'll do the same thing to the second equation, and we get x equals 1. So x equals 16 or x equals 1. We should check these because rational exponents or radicals are involved. 16 to the 1/2 minus 3 times 16 to the 1/4 plus 2, does that equal 0? 16 to the 1/2 is 4. 16 to the 1/4 is 2. So 4 minus 3 times 2 plus 2, does that equal 0? 4 minus 6 plus 2, does that equal 0? Yes, it does. So x equals 16 works. Let's check x equals 1. 1 to the 1/2 minus 3 times 1 to the 1/4 plus 2, does that equal 0? 1 to the 1/2 power is 1. 1 to the 1/4 power is 1. 1 minus 3 times 1 plus 2, does that equal 0? 1 minus 3 plus 2, does that equal 0? Yes, it does. So both of these work. So x can be 16 or x can be 1. Okay, we have another example. 2 to the x to the negative 2 power minus 3 times x to the negative 1 power minus 4 equals 0. Now, we could write this as a rational equation, but we could also recognize that this is in quadratic form. I could set u equal to x to the negative 1/2 power. And then u squared will be x to the negative 2 power. Substituting in, we get 2u squared minus 3u minus 4 equals 0. Now this is quadratic, but it doesn't factor. So let's solve this using the quadratic formula. And we could have done that for any of the other quadratic equations as well. But usually if you're good at factoring, factoring is faster than the quadratic formula. So here a is 2, b is negative 3, c is negative 4. Substituting in, u equals the opposite of negative 3 plus or minus the square root of negative 3 squared minus 4 times 2 times negative 4 all over 2 times 2. Or u equals 3 plus or minus the square root of 9 plus 32 all over 4. Or 3 plus or minus the square root of 41 over 4. So these are our two answers for what u is. But now we need to substitute x squared in for u. So I have, x to the negative 1 in for u. I have x to the negative 1 equals 3 plus the square root of 41 over 4. And then x to the negative 1 equals 3 minus the square root of 41 over 4. We need to solve both of these for x. So let's raise both sides to the reciprocal exponent. What's the reciprocal of negative 1? Negative 1. So on the left side I have x. And if I raise the right-hand side to the negative 1 power, I am taking the reciprocal, which gives me 4 over 3 plus the square root of 41. But we need to rationalize the denominator. So we will multiply by 3 minus the square root of 41 over 3 minus the square root of 41. When we distribute, we get 12 minus 4 radical 41 over 9 minus 3 radical 41 plus 3 radical 41 minus 41. Simplifying, I'm drawing the line because I'm not looking at the second equation yet. We're still working on finishing this first one, and I didn't want it to look like it was combined. So here we have 12 minus 4 radical 41. Combining like terms, well, the radical terms cancel out, and then we have 9 minus 41, which is negative 32. Okay, we could factor 4 out of everything. So when I factor 4 out of the numerator, I'm left with 3 minus radical 41 inside the parentheses. When I factor 4 out of the denominator, I'm left with negative 8. The 4's can cancel. And here, one of my values for x is 3 minus the square root of 41 over negative 8. Now, in terms of checking this one, and I still have to solve the other one, because we have negative exponents here, I do need to make sure that when I put this value in for x, I won't have 0 in the denominator. This value is definitely not 0, so I'm not making a denominator 0, so it is not extraneous. This is a solution. My other solution I'll do on the next slide. So we're solving x to the negative 1 equals 3 minus the square root of 41 over 4. We're going to raise both sides to the negative 1 power again. So x equals 4 over 3 minus the square root of 41. Again, we need to rationalize the denominator. I'll multiply by 3 plus the square root of 41 over 3 plus the square root of 41. And then we'll multiply or distribute. We will have 12 plus 4 radical 41 over 9 plus 3 radical 41 minus 3 radical 41 minus 41. So I have 12 plus 4 radical 41 My radicals cancel out again. 9 minus 41 is negative 32. And then if I factor 4 out of the numerator, I'm left with 3 plus the square root of 41 in parentheses. If I factor 4 out of the denominator, I have negative 8. If I cancel the 4's, my second solution is 3 plus the square root of 41 over negative 8. So my two solutions are 3 plus or minus the square root of 41 all over negative 8.